All right, well, so the first lecture we're going to start off with for the rest of the semester here is just kind of review what we've been talking about with the hydrogen atom. Okay, so just kind of simple review here, large overview, right? Before the long break, we introduced the hydrogen atom Hamiltonian, right? We derived and found the Schrödinger equation for the hydrogen atom, separated variables to have a radial part, right, and an angular part, okay, right. We use center mass coordinates, right, in order to get to this final solution, right. We just didn't care about the center mass motion, right, because that's just translational motion of the overall atom in some container. Doesn't really matter, right? What we're interested in is the energy of the electron and the properties and the interaction of the electron with the nucleus, right? How is it rotating around the nucleus and things like that, right? And so that's what we care about. And then we did separation of variables, right, to again end up with the radial equation and the angular equation, right? Where the angular part is your spherical harmonics, the radial part we solved for. Right, and the solution to this hydrogen atom Hamiltonian is the energy given here, right, which has a bunch of constants, doesn't really matter too much, right? Z here is your nuclear charge, and N is your quantum number, okay? So Z being nuclear charge, I guess I should say your atomic number, right? Hydrogen is 1, helium is 2, carbon is 6, so on and so forth, right? So the Z here isn't necessarily the charge of your atom, right, but the number of protons in your nucleus, okay? And again, is your quantum number. And then our wave function, right, because of the separation of variables, can be broken up into a radial part, right, and an angular part, where again, the angular part is spherical harmonics, and the radial part is some complex function, right, but the radial part does have, right, this radial part of the wave function, you know, has some stuff, and then it does have an exponential decay with respect to r, right? So the radial part does have this exponential decay, right? But it looks different depending on your quantum numbers n and l, right? And so yeah, right. And then the quantum numbers, right, out of the solutions of the Hamiltonian are your principal quantum number, right? N, that's giving you your total energy. L, right, is your angular momentum quantum number. That's going to be your total angular momentum quantum, right? And N sub L is referred to as like the magnetic quantum number. That's the angular momentum in the z direction, right? As we talked about angular momentum before, right? I can't know angular momentum in all directions at the same time because those operators do not commute, right? The Heisenberg uncertainty principle. And so we just picked the z just because. Right, sort of arbitrary which direction you pick. So we pick the z direction, and the total angular momentum is the two quantum numbers that we're able to know, the two things that we can measure precisely and exactly if we are able to in experiments, right? And again, right, because this Heisenberg uncertainty principle, all of our total angular momentum can't be in one direction, right? So the magnitude of the angular momentum in the z direction is always going to be less than the total angular momentum, okay? And then the final quantum number here I have written down that we'll talk about in the next video is electron spin quantum number, okay? N sub s, and this is defining the spin in the z direction, sort of like M sub L is the angular momentum in the z direction, this is the spin electron in the z direction. And we'll talk more about that in the next video. Okay, but before we get to that, we'll just, again, review properties of the hydrogen atom, right? The wave function, again, has this general form, right? The number of nodes total is n minus 1, but those nodes can be broken down into radial nodes and angular nodes, right? So a radial node is a node where the total wave function here, right, when r equals some value, the total wave function is 0, right? So you can imagine that's basically a radial node is going to look like the surface of a sphere, right? That's what a radial node is going to look like, because it's at every r distance, no matter what your angles are, your wave function is 0, right? That's for a radial node, right? For your angular nodes here, okay, right, that is when some value of theta is, theta naught, or phi equals phi naught, right? Some values of theta or phi, right? Then your wave function equals 0, right? And for angular nodes, those are going to look more like planes in space, right? Some just two-dimensional planes, some slice through space, right? Take a knife and slice it through space, right? And that will give you your kind of radial nodes, right? If you then extend, depending on the node, it might be not just a plane, it could be, like a cone or something like that for like your p orbitals or things of that nature. So, the angular nodes can have slightly different shapes, but yeah. And then the wave functions, right? We talk about our 1s orbitals, our 2s orbitals, 2p orbitals, right? And it's just a reminder, right? Those s, p, d, f, g, right? Those names are corresponding to the L quantum number, right? So this is the L quantum number, right? L equals 0, that's referring to s orbital. L equals 1, that's the p orbital. L equals 2, that's the d orbital, so on and so forth. Okay. And with the radial part of the wave function, when we're talking about what is the probability distribution of the electron around the hydrogen atom, right? We discussed how probability distribution, right, is given, right, by psi star psi, right? That's your probability distribution, psi star psi, okay, right? Well, for the hydrogen atom, right, we're using polar coordinates, spherical coordinates, right? And so because of that, there's this extra factor of r squared that pops up, okay? So the actual probability distribution in the r direction is given by the radial part of the wave function times its complex conjugate, which is kind of your normal thing, times this r squared, right? And so what that means is that, right, there's, for every single orbital, right, every single wave function an electron can occupy, right, it's going to have 0 probability of being at the nucleus, which is good, right? We shouldn't expect the electron to be exactly on top of the nucleus, right? Because of the exponential decay of your radial part of your wave function, right? This goes to 0 as r goes to infinity as well. That's good, right? And then because you're starting at 0, right? R equals 0, you're starting at 0. R equals infinity, you're at 0, right? Your wave function is going to have some non-zero value between there, and it's going to have some maximum point, right? What we talked about.